Good afternoon, everyone. Myself Sana Sheikh, a fourth year PhD student from IIT Bombay. I am going to take your live session for the course of NPTEL, which is entitled as Symmetry, Stereochemistry and Applications. And the course instructor is Professor Anshuman Roy Chaudhary from IISER Mohali. In today's class, we are going to discuss the questions based on the group theory. As we have already discussed in previous live session that the IUPAC nomenclature and their structures. So now we are moving towards the stereochemistry and symmetry part. So that's why in this class we are going to cover the point group theory. So let's move to the question here. The first question is given here. Determine the point group of the following molecule. Can you name this molecule? Yeah, IUPAC nomenclature I have taught you, right? So this is this is halo group attached here, 4 different halo groups. So here we will start the giving numbering. First of all, we have to give the number 1 to any of the carbon next to the halogen atom. So here we are writing 1. Then always move to the side where the next halogen atom is there. You cannot give this number 2. So give number this carbon will become 2. 3, 4, 5. So the structure will become 1, 2, 4, 5, 'tetra bromobenzene. Okay, this is a tetra bromobenzene. Now we have to find out the different point group or symmetry element. We can say what is point group. The main question is here, what is point group? Anybody knows about it? Anyone? The point group is a nothing but a collection of symmetry operations that can be performed on the molecule to produce a conformation that is identical to the original one, or we can say indistinguishable from the original one. That is called a point group. So what are different symmetry operations? So there are various different symmetry operations, like E denote the identical, like you don't have to do anything on the molecule, so that will comes under E symmetry operation. Then axis of symmetry. What is axis of symmetry? Next is axis of symmetry. And the axis of symmetry is denoted by Cn. N is number of rotation. I will explain one by one. Then next is plane of symmetry. So plane is denoted by sigma. N is again the number of fold. Okay. So these are different symmetry operations we are going to discuss in this class. I is inversion point. Inversion. When we will solve the question along with the discussion of these symmetry operations. So in this molecule, now just start this molecule's point group. Here you can see that the molecule have this structure in 3D, right? Are you agree with me? This is the 3D structure. Now in this 3D structure, you can see that this red atom is bromide and this is our benzene ring. All of you know that because of double bond in 3 double bond in benzene ring, the benzene ring is planar. Planar means it is on a plane of paper. Planar. Because of this planar ring, all the bromide atom are on plane only, on the same plane. So if you will see that we can cut this from here, right? If I am cutting it here or passing a plane, suppose I am passing a plane here, so this part is same like this one, right? There is a symmetry, correct? So here we have plane of symmetry, right? Sigma plane is present. Now find out the symmetry axis. Is there any symmetry axis? Same here only. If you will rotate this molecule by 180, right? 180 on this axis. Okay, clockwise or counterclockwise as your wish. But if you will rotate by 180, you will get the same molecule like which will look like this one only. But this atom will comes this side and this will go that side, right? So this is also a indistinguishable structure. So that's why here symmetry element is also present, which is C2 symmetry. C2, right? Are you agree with me? Okay, the next symmetry element, other symmetry element we have to find out here is subsidiary axis. So listen here. First of all, we have here two types of symmetry axis. One is principal symmetry axis, principal, and the second one is subsidiary. Subsidiary. Okay, what is principal symmetry axis and what is subsidiary subsidiary symmetry axis? Sorry. So talking about the principal one, when the maximum number of fold is present in principal symmetry axis. Like if we have other molecules, like suppose we have ammonia, right? This is the, no, we'll take something else. Yeah. Okay. I'm taking the same. Suppose we have suppose we have this molecule. Okay. And if we will rotate on this axis here, imagine in 3D. So these three chloride ion are away from each other by 120 degree. Are you agree with this one? Correct? 120 degree, right? Because 360 circle is there. So they are away from not exactly 120, 108 angle is there. But if we will see from top side, I'm asking angle between these two chlorine. I'm not giving an answer for this one. But if you are looking on top side, these three methyl are looking like this one, this way. Correct? Chloride, 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 and this is carbon which is going behind. Am I right? So if here these three chloride are looking like this way, so if I will rotate this by 120 degree, this chloride 1, 2, 3, so one will go become 2, one will go at the position of 2, 2 will go to the third position, third will go to the first position. So but both all the atoms are chloride atoms, so it will look like indistinguishable. We are able to distinguish between these chloride because we are giving number to them. But if we will not give the number, then it will become indistinguishable. Correct? Indistinguishable. Now because 120 degree rotation is giving our same molecule which is identical or indistinguishable from the original one. So we will do the one thing, 360 divided by 120, because 360 circle is there, we will get 3. So we have 3 fold of axis in this case. So in this case it will become the C3 axis. Now we have to find out which is principal axis, which is subsidiary axis, right? This is C3 fold axis. Now any other axis is present in this molecule? Yeah, we can pass the axis here, and if you will rotate by 180 degree, this carbon will come to this side and this will go this side, and we will get the again indistinguishable structure, right? Indistinguishable structure, but in this case carbon is going to change. Here carbon was remaining same, only the other substituent was rotating. Here carbon is rotating, but still the structure is indistinguishable, right? So this is 180 rotation. So 360 divided by 180 will become 2. So C2 axis, correct? Now we got two different axes from this molecule. So the number of fold in the axis which is more we will call them a principal axis. Number of fold here, because C2 is 2 is less than 3, that's why it is subsidiary axis, small axis we can say, subsidiary axis. So the axis with maximum number of fold will be considered as a principal axis. I hope this example is clear to you. So always principal axis number is comes in point group. Whenever we are deciding the point group, we are considering the principal axis number of fold. Okay. Now let's solve this question. Okay. So here we got C2 axis, right? C2 axis. Any other plane of symmetry is present? Sorry, axis of symmetry is present? Yes. We can pass the axis here in between this one. And if we will rotate by 180, right, again we will get the indistinguishable structure, which is again a C2 axis. So here listen one more thing. Principal axis and subsidiary axis are perpendicular to each other. Perpendicular to each other. Principal axis and subsidiary axis. Remember this point also. So here we have two different axes which are perpendicular to each other here. So one is principal axis and one is subsidiary axis. So how we will find out which one is principal axis and which one is subsidiary axis? In this case, we cannot differentiate between principal and subsidiary axis because the number of fold is same in both the axes. So we will consider there are two C2 axes are present in this molecule. Okay. Many other are also there, but here we are considering this way. Okay. Now let's consider the plane of symmetry present in this molecule. So whenever the perpendicular, remember one more point here. Sorry. Okay. Whenever these two perpendicular axes are present, we are writing that point group with D. Denoted by D. D means both the principal and subsidiary axes are present in the molecule D. Now we know that we have two fold of symmetry axis, right? That's why it will become D2. D2. Now next thing, the point group will be decided on the basis of plane. If we have had a horizontal plane, it will become D2H. If we have vertical plane, it will become D2V. If we have horizontal plane, it will become H. And if it will contain both the vertical and horizontal plane, it will denoted by H only. And dihedral plane will be there that time D. Okay. We will learn each and everything by discussing the question. Okay. Now here, can you imagine the plane in this molecule? Any plane? Suppose I will pass the plane like this on plane of paper, right? Half molecule is below the paper, half molecule is above the paper, right? And if I will cut down the molecule, so each and every atom will be divided into two, right? Cut karna hai exactly in half. We will cut exactly in a half, so we will get the same molecule, right? If we will cut this way, this plane will be parallel to this axis, right? So this is the vertical plane, the plane which is in a same plane with the principal axis or a axis of rotation is called as a vertical plane. Vertical plane, direction is same. And if we will pass the plane this way, right? This is also a plane, but it is perpendicular to the principal axis. So this is called as a horizontal plane. Horizontal plane, right? Horizontal plane. So because in this molecule both the plane are present, vertical as well as horizontal, that's why we will write here H. Symmetry will become H. So the point group for this molecule is D2H. You have to imagine in 3D for this type of question. So please try yourself and then try to solve this question. Okay. Now next move to the next question. Yeah. Here we have to find out the point group. So you can see that here we have metal and this is ligand. This ligand is bidentate ligand. 3 ligand is there, right? So the structure will look like this one, this way. So metal is in between, and this diethyldiamine will be coordinate by nitrogen atom to the metal, right? So this is octahedral complex. Octahedral complex. Why octahedral complex? 6 coordinating site is available. 6 coordination. Okay. So that's why it is octahedral complex. Now all of you can see that because of bidentate ligand is the binding is different. This is wedge bond, this is dash bond, right? So if you will imagine in 3D, it will look like completely different. But first of all, we will find out the principal axis. So just imagine the molecule this way only. Now we have here this red dot. This red dot is a center axis of the symmetry, which is going below the plane. Suppose it's going straight. We are looking the molecule from the top side. From the top side, okay? If we are looking from the top side, this is looking like this dot is like not dot only. This is the axis which is going downside. Okay, this is the axis. If we will rotate on this axis by 120 degree, suppose this is the wait the angle between these two wedge bond of nitrogen is 120, correct? If we will rotate this by 120, suppose we are moving clockwise, okay, clockwise this way. So this nitrogen will take place at this position. It will come on this position, and this nitrogen will come in on this position, right? So 120 rotation will make the molecule look like indistinguishable from the original one, but not the identical. Okay, indistinguishable. So because after the rotation the molecule will look like same as it was looking earlier, so that's why this is called as a axis of symmetry. Axis of symmetry. Because the angle is 120, that's why the axis will become C3. Okay, C3, threefold of axis. Now we have to find out the different subsidiary axis also. Because the molecule is in 3D, it's difficult to imagine here, but I will show one image here. You can see that okay, here you can see that this is a principal axis I was talking about. We were looking from this top side, that's why this was looking like a red dot. Okay, red dot. So this is a C3 axis. When you are rotating by 120, I was talking about the angle between these two was 120. Okay, and rotation was making the molecule like indistinguishable. That's why we were able to say that here C3 principal axis is present. Okay, C3 principal axis is present. Now let's talk about the subsidiary axis. I hope this one is clear to all of you, right? Now here we have same molecule, right? But the axis is passing between the these two molecules. I will tell you. Suppose this is a principal axis, so this is perpendicular to that axis, perpendicular. Okay, so it will pass through the this point and sorry this point, like okay. Okay, so this axis is passing through here, and if we will rotate from this axis by 180 degree, if you rotate the axis by 180 degree, here we have a wedge bond, right? On that side also the bond is there, which is hidden in backside to this bond, right? Backside to this bond is one bond is there, right? If you will rotate it by 180, this bond will take the position of this one, and this will come to this side, right? Like this way. You have to imagine in 3D. It's difficult to explain in plane of paper, so that's why I'm explaining this way, right? Imagine the backside bond here is there, okay? And after the rotation, this will come this side, and this bond will come, this bond will take the position of this bond. Okay, so this is a C2 axis because of 180 rotation. So here all of you are clear here that we have two types of axis, principal axis and subsidiary axis. Here principal axis is C3 and subsidiary axis is C2. C2. Remember, E is present in all the element because E means identical. Identical means 360 rotation. 360 rotation is present in all the molecules. So E symmetry element is always, you have to consider always E element. Okay, E group. Now talking about the C1. C1 is also present in all the molecule because 360 rotation. This is E means nothing, no symmetry element is applied, so identical. C1 means the rotation of 360, so E in C1 is always present. Now let's talk about the other symmetry element. We have found out that C3 axis is present in this molecule and subsidiary axes are also present. So three C2 axes are present, three subsidiary axes. You can see here 1, 2 and 3, right? Three subsidiary axes are present here. You can see the molecule here also, and you can imagine in 3D. So because we have two different types of axis, principal and subsidiary axis, it will be the point group will be donated by D. Now because the principal axis is 3, we will write here 3. Okay. Now let's find out the plane of symmetry. Can you find any plane here in this molecule? If we will pass the plane from top side, suppose from parallel to the principal axis, right? So if we will pass the plane here this way, this side is different and this side is different. Both the sides are different, so this is not the plane of symmetry. Symmetry will not be present after passing the plane. If you will pass the plane from C2 axis side, again you will not get the same thing because this bond is this side and this is on other side. If you will pass the plane, they will be on opposite side, not the same side. Okay, so that's why here plane of symmetry is not present. You can check yourself also. There is no plane of symmetry. If you will pass the plane, you will not get the indistinguishable image. So that's why plane of symmetry is absent in this case. That's because of absence of the plane of symmetry, we will not write any significance of plane of symmetry. Okay, so the point group will become only D3. We will not write H or V or anything which is denoting the plane. So the point group will become D3 in this case. Next question. What's the name of this molecule? The name of the molecule you have to find out. I have already explained in IUPAC TA class. So here I will directly write down the name. dichloroethene. Okay, dichloroethene. Here we have to find out the symmetry element. Suppose we are considering the molecule in this plane. Okay, plane. This is our paper. Okay, plane of paper or board of whatever you are considering. You can consider. Okay, or screen. But if we will pass the plane from here, I will show this by dot because it's going downside and coming outside. Wedge line I will show wedge line. Okay. This is downside, backside. So this is the plane. This is the axis which is present in this molecule. And if you will rotate the axis by 120 degree, you will see that this Cl2 will take the position of Cl1 and this Cl1 will rotate it after rotation goes to the position of Cl1. Okay. So here you can see the rotation after 120 rotation you are getting the indistinguishable compound. So that means here C2 symmetry is present. Right, C2 symmetry is present. Now this is the axis you got here. Now let's find out any other axis is present which is perpendicular to this axis. So the one more possibility we can do this one, but here if you will rotate the molecule by 120 or whatever degree, you will not get the same molecule because this Cl will goes to this side H and H will come here, right, which is not the same. Atom should be remain same after the rotation. So here it is not the case. That's why this axis is not present. Only C2 axis is present, right? Only C2 axis. Principal axis is not there. When the principal axis is not there, only one type of symmetry axis is present. That time we are initiating our point group by C only. In earlier cases we were writing D. Why we are writing D? Because there was a principal axis along with the subsidiary axis present in the molecule. But here only one axis is present. We will consider principal axis only, and the two-fold axis is there. That's why we are writing 2 C2. Okay. Now let's talk about the plane of symmetry. Any plane of symmetry you can see here? Yeah, this plane, right? This plane is passing in the same plane of the paper or screen, whatever you are considering, right? So all the atom will become half, like this atom is here, this is here. It will cut down between the half, all the atoms. The plane will pass through the all the atom, so it will be cut it into half. So that's why there is a plane is present, but the plane is perpendicular to the axis of symmetry, right? This is the plane only. The plane is present here. Okay, and this plane is perpendicular to the C2 axis, so that means we will consider it as a horizontal plane. Right, horizontal plane. So because horizontal plane is present only, there is no vertical plane, we will write here C2H. The point group for this molecule is C2H. I hope all of you are clear. Next, move to the next question. Yeah, this is the allene. all of you can see, Aline. Here we have two double bonds present in the molecule, which looks like this one. You can see this image, and if you will see these two molecules, these two groups are perpendicular to these two groups, right? You can see in 3D. The image is given, video is here. You can imagine the molecule here, right? Now, if we will pass the C2 axis, you can see C2 axis here with the red line here, right? C2 axis. Okay. After the rotation, the molecule is look like same. You can see here, right? C2 axis passed. How the C2 axis is passing? You can see one molecule is, if I am looking from the top face, this carbon here, you can see that if I will pass the here C2 axis, after the rotation on this axis, this CH3 will take this position, this one. You can see here in this case. So here one C2 axis is passing from this carbon, and one is on the passing through all the three carbon. So there are two C2 axes present. It's very difficult to explain in online class because this is a stereochemistry type of molecule, stereochemistry symmetry molecule. So you have to imagine in 3D. I can't explain well in plane of paper, but still I'm trying to do by this image here. Okay. Yeah. So here there are two C2 axes present. One is principal and one is subsidiary axis. So that's why the point group is D. Okay. D2. Is there any plane of symmetry? No, because of the alene system have both the different group on opposite side or perpendicular. We don't have any symmetry element here. Only the axis of symmetry is present. There is no symmetry element. So that's why the point group of this alene system is D2. Now the next question is, what is the name of this compound? Tetrabromobutane. Okay, tetrabromobutane. In this tetrabromobutane, you can see that all the bromo atom are have opposite stereochemistry. This is upside, this is downside if we are considering this cyclobutane on plane. So all the bromide atom have different stereochemistry. Okay, so here in 3D you can imagine this is our cyclobutane. Sorry, this is 4 carbon of cyclobutane. One is behind this one here. here and here and this way. Okay, this is the cyclobutane. Now on suppose we are considering this carbon as this one. So bromide is going downside here, and next carbon is this one where it is going upside here, upside, right? And then again here it downside, here it is downside, then this one is the upside here. Okay, imagine in this case like this way. I hope you are able to imagine this molecule. Now we will pass the symmetry element here. What symmetry element is present here? If we will consider here, okay, first of all we will find the axis of symmetry. Okay, if the axis is here, okay, and we will rotate by 180 degree, this will comes to this side and this will go this way, right? And same in case of downside also, right? 180 degrees. So here C2 axis is present. Are you getting it? C2 axis will be there. Then now we have to find out the principal axis or the other axis which is perpendicular to this C2 axis. Any other axis is present? Yes, if we will pass the axis through here, this side, and we will move C2, we will do the C2 symmetry, rotation by C2, this will comes to this side, right? And this bromide will go to this side, like this way. So here perpendicular C2 axis is again present. So there are two axes, principal and subsidiary axis, and both the fold of axis is C2 only. So that's why we will write here D2, right? D2. Now we have to find out the plane of symmetry. Suppose here we will cut the molecule into two halves like this from here. Okay, here. So this half is same to this half, right? Both the halves are same, and in both the cases the bromide group is upside only, right? So here plane of symmetry is present, correct? Plane of symmetry is present. And talking about the other plane which is perpendicular to the principal axis, is there any plane? This was the principal axis. No, sorry. Okay, here if we will pass the plane perpendicular to this one, this plane will not give the same molecule downside, right? Downside is not the same thing which is upside. So that's why this horizontal plane is not present in this case. Only a vertical plane is present which is parallel to the principal axis. Okay, so vertical plane is present, there is no horizontal plane, that's why we will write here D2V. D2V. The point group for this one will become a D2V. Okay. The next question is, draw the Newmann projection of the following molecules using the C star C star bond as the axis of the molecule in the eclipse conformation. Here we have the molecule with 4 carbon, that means butane, right? So butane, here we have these 2 star carbons. We have to convert this in a Newmann projection. So whenever you have to convert in the Newmann projection in an eclipse form or a whatever staggered form, you have to look the molecule from either side, one side. Either you can look from this side or you can look from this side. Suppose here I am considering this way look, only this side. Both the side are same, so we cannot distinguish between them. That's why I am considering only one side here. Both the sides are same. Okay. Now you have to make the carbon which is nearest to your side. Suppose if I am looking from this side, that means this is the first carbon. First carbon will always be denoted by dot only. Denoted by dot only. Okay. Then the next carbon which is behind this carbon, if you are looking from this plane, right? So this next second carbon is exactly behind the first carbon, right? So because this is behind the second carbon, and if we will denote by dot only, we will not be able to distinguish between them. That's why we are showing a circle. Circle is nothing but our second carbon. We are just showing bigger to distinguish or differentiate between them. Okay. Now on first carbon, how many groups are there? Hydrogen, correct? So here I will write this way, hydrogen, and one is CH3. This is CH3. Now let's talk about the second carbon. Here we have second carbon, and you can see this methyl group is here upside, CH3, and 2 other group are hydrogen. Okay, this is the staggered form. Now the question is that draw the Newmann projection of the following molecule using the CC bond as the axis of the molecule in an eclipse conformation. This is the staggered one. What is eclipse conformation? When one molecule will be overlap with the other molecule on different carbon, that is called the eclipse conformation. That means each and every atom are behind the other atom, like these 2 carbon are on same plane, right? Same side, like this first carbon is just above the second carbon, right? Just same plane. Same way, if we will have write molecule this way, these two carbon, and if we are looking from this side, these 2 carbon are same side, and these 2 methyl group are also overlapping. So all the hydrogen atom will also overlap. So this is called a eclipse form. So how we will convert in this in a eclipse form? I will write here. You have to keep one carbon as it is, and you have to rotate the other carbon. Carbon free rotation will be there. So here I am considering this carbon as it is, and I will rotate the backside carbon by 180 degree. 180 degree rotation. Okay, not exactly 180 degree. You can rotate by suppose this is the next bond, okay, on first carbon. So this bond will rotate by 60 degree to come on this position, right? 60 degree. So it will become on other side. CH3 H H. Now we have rotated the backside atoms, or at same position CH3 will be there. H H, correct? So all are on same position. This is called eclipse conformation. Eclipse. This is staggered. So this is one form of eclipse conformation. How many eclipse conformations are possible here? If again this CH3 will be rotated by 120 degree, you will get the here CH3 H and H. This is also eclipse one. And again, if you will rotate this backside carbon by 120 degree, you will get the third possible structure, which will look like this way. This CH3 will be rotated by 120 degree again. So here CH3 H and H. Okay, so these are three different types of eclipse conformation possible in this structure by Newmann projection. I hope all of you are clear here. These three eclipse conformation we got here. Okay. We started with staggered conformation, then we have made it eclipsed, anticlinical, and then staggered Gaussian when the two methyl group are next to each other, and in staggered conformation, that time it's called a Gauss interaction, when both the methyl group are opposite side to each other and giving a 180 degree angle. That time it's called as an anti-staggered form. And in eclipse conformation, when both the methyl group are away from each other and present in eclipse form, that is called the anticlinical. And when both the methyl group are overlapping on each other, that is called a synperiplanar. Okay. Next question. Yeah. Here again we have the same molecule, but we have to take the carbon 1 2 carbon instead of 2 3. Okay. That time we were taking these 2 3 carbon atom, right? Here we have to take 1 2 carbon atom. We have to consider 1 2 carbon atom and have to draw the cyclobutane Newmann projection. Sorry, not cyclobutane. I'm sorry for this one. 1 2 butane Newmann projection. Okay. So if we will consider these two carbon, and I'm looking from this side, right? One carbon is, this carbon is front side carbon. and this is the back side. Okay. So as you can see, this carbon have all the 3 substituent as hydrogen atom. So here I will write H, H, H. Now the next carbon is backside one. I will draw this way. Or I can draw directly eclipse form also, but here I am showing easiest way. So here we on this carbon we have these two carbon, which is C2H5, correct? Ethane group. So I will write here C2H5. Here H, here H. Okay. So this is the staggered form. If I want to convert this in eclipse form, I will rotate the back carbon by 60 degree. This is the eclipse form. And in this case, only one possibility of eclipse plane eclipse form is there, because all the atom present on first carbon are identical. All the atom are H only. So only one type of eclipse interaction is possible here, which is C2H5 and H interaction. This type of interaction. There is no other group is present on the molecule. That's why. Okay. Got it? Now next question. Yeah, this is the pentane molecule, right? Pentane. 1, 2, 3, 4, 5. Here we have to consider these two carbon atoms. I will take here like dot this second carbon as a dot, then this is the third carbon backside. Okay. This one. Now we have CH3 here, this CH3 and 2H. Okay. Now on backside carbon, one C2H5 group is there. This one, right? So I will write here C2H5. This is staggered. Now we have to write the eclipse form. How you will write the eclipse form? Just keep one carbon as it is and rotate the other carbon by 60 degree. You can rotate any of carbon. You can rotate the first carbon by keeping the backside carbon as it is, or you can rotate the backside carbon by keeping the first carbon as it is. So here what I will do, I will rotate the backside carbon only. I will keep the front carbon as it is. If I will rotate this by 60 degree, okay, then again rotation of this backside bond by 120 degree. For eclipse confirmation, I am not showing the staggered one. For staggered one, you have to rotate by 60 degree. From eclipse to staggered or staggered to eclipse, always rotate the one carbon by 60 degree. But if you want to convert the staggered to staggered or eclipse to eclipse form, that time the rotation should be of 120 degree angle. So here, because I want to make the eclipse confirmation, that's why I am rotating it by 120 degree. I'm keeping the front carbon as it is. After the rotation, it's become situation H and H. Okay, so this is called a anti-periplanar. Anti-periplanar. Okay, now again I have to convert this into a next another eclipse form. First carbon as it is. Now the rotation is on the backside carbon atom. Okay, so if you will see that these two cases are same and clinical structure, right? Because both the C2H5 and CH3 group are on other side, adjacent side apart from 180 degree, and it's overlapping with the hydrogen atom. So this is a clinical structure. But in this case only, second case only, 1 3 are same. Okay, second case, these CH3 group and C2H5 group are overlapping each other. So that is an anti-periplanar structure. So that's why here two types of eclipse conformation is present. Okay, one is anti-periplanar, one is clinical. So I hope all of you understood how you can convert from staggered to eclipse conformation and how many eclipse conformation you can find out here. Right? This is A1 is our 2. We have discussed here. This C and E are same. Next question. What is this structure? Cyclohexane. Cyclohexane is naturally present in which form? Which conformation? How many conformations are there for cyclohexane? Chair, boat, half chair, half boat, twisted chair, and many more. These type of conformations are there. Here we have to find out the Newmann projection of these 4 star carbon atom, right? So first of all, we have to find out which conformation is it, this one. So as all of you know that this is the chair form. Okay, and in boat form we have this flagpole interaction, right? Flagpole interaction we called it. So in boat form, both these carbon are on same side. This is like a chair. So here you can see that here we have this type of hydrogens, right? So this is a boat conformation. Boat conformation. Okay. Next example of boat conformation. What is the difference between conformation and configuration? This is a homework for all of you. Tell me next time. Difference between conformation and configuration. Okay. Here you can see that as I told you, flag pole interaction are there, right here in between these two carbons. So this is a Gauss interaction. This is a chair conformation. Sorry. Again, boat. Okay, it's a boat conformation, and we are here drawing a Newman projection. So here Newman projection is between these carbon and this carbon. One is behind the other carbon, right? So this, suppose I am considering here 1 2, sorry for mistake. This Newman projection is always drawn between two adjacent carbon, right? If I will consider this carbon as 1, then 2, 3, 4, 5,